this computer. There we go. Okay. Over just a little. Okay, I'm gonna have to move my mark. Be over here. Here. There it is. That's so I don't write something over here that's not recorded. Tells me how far I can go. Okay. So for the next exam, which would be the third one, we'll cover chapter 7 and 8 in your textbook. Gases, liquids, and solids, and solutions. So there's 7. Let's see, where's 8? There's 8. Nah, maybe I put it together. Oh, there it is. Oh, but I don't have the questions. All I have is the answers from the problems in your book. Okay. So you're going to have to give me the questions, whichever ones you want to do. This is, you guys are in charge of the review. Any concepts that are bothering you? I could look through here and see what the major things are. Gases, liquids, and solids. So we have all the gas laws to begin with. Then we have a kinetic molecular theory that explains the laws. Then a description of the evaporation process, vapor pressures, boiling points. That's just chapter 7. Okay, got questions? Or do I need to just start talking and then maybe something will click?
I'm marked to go back over Daltons Law, but honestly, I feel like it would be helpful if you just went kind of like touch back on all the gas laws.
Okay. All right. So, and the gas laws, as we present them, are basically in chronological order. In other words, the earliest one is Boyles Law. And the reason for that is they didn't have the technology to study gases except in terms of pressure and volume. So Boyles Law just says that pressure times volume is equal to a constant value. And anytime you have the product of two values equal to a constant, you have an inverse relationship. So if we graph this on a scale like that, you're going to get a hyperbola. Okay? So, and scientists hate curves. But when we can get a straight line, it's a lot better. So what we do is we take this and solve it for P. And then we separate out the V like this. Okay. So that is in the form of, this is Y equals, that's the slope, and that's the X. Okay, and Y equals mx plus b on the straight line. But the b in this case is 0, because the line will go through the origin. So if we plot, get this out of the way, if we plot pressure against 1 over volume, in this case, x is the inverse of volume. So P goes up here. Then we get a straight line. And the slope of that line is equal to K. Simply from this relationship. That's why we did that inverse of V. Now, this is not practical for solving problems. Well, this is. But for solving problems, there are 2 approaches. And I call it the before and after. Right? So if you say P times V equals a constant, under those conditions, beginning conditions, and then you have ending conditions. Oops, it's not right. Then P times V is always equal to that constant, right? So if this one's equal to the constant, and that one's equal to the constant, then they're equal to each other. So that's why P1 equals P2 P2. And if you know beginning conditions, ending conditions, all you need is one unknown and you can solve for it. Okay? You just have to be sure that you get them in the right place. That's why when I read a word problem, I just write them on the side here. And then I say, look at the problem and say, what's the beginning, what's the end? Sometimes you might say initial and final, whatever suits you. But as long as you get those values in the right place, then you can plug them in the formula and it'll work. But if you try to do it in your head, sometimes you get them switched around. Now, you don't have to have standard units here. You can have anything, any expression of pressure will do. Any expression of volume will do. So, for example, we could have atmospheres here, we could have pounds per square inch, we could have millimeters of mercury, and volume we could have milliliters, we could have liters, we could have quarts. It would still work. You just, whatever units you choose, the answer will come out in that unit. Okay, so that's Boyles Law. And Boyles Law works, remember there are 4 variables that we use to define the conditions of a gas, the state, to describe a gas: pressure, volume, temperature, and number of moles, that is the amount of gas. Right? So if we let these 2 vary, right here and here, these have to be constant. Those 2 have to be held constant. Hang it all over, temperature constant, number of moles constant. Then you can let these 2 vary.
So if you hold like pressure and volume constant, you can let temperature and moles vary?
Exactly.
Okay.
Right. So remember how Boyle held his number of moles constant. He had that J tube. Right. And he started adding mercury to it. And it would come down here and settle in the bottom. And then he'd add a little more and a little more. And once it touched the inside curve, then this gas is trapped. And that trapped gas, assuming there are no breaks in the tube, will hold the moles constant. Okay? Temperature constant, how would he do that? Because they didn't have a good way to measure temperature at this time. But they knew how to keep temperature constant. One way would be an ice bath. Just mix ice and water together, and as long as there's water and ice together, it'll be a constant temperature, and you can just submerge a tube in it. Or if you lived in a fancy house in those days, and Boyle was rich enough, the houses in England at that time were made out of masonry, either brick or stone. And if you've ever been in a cave, you know how constant temperature is with stone walls. If you go into a cave in the winter, the cave feels warm. If you go in the summer, the cave feels cool. That's because it's constant temperature all year round. And the houses were like that. Of course, that made them hard to heat in the winter, but that's where tapestries and rugs come in. But you can hold the temperature and moles constant very easily, and Boyle did that. Okay, so let's see, that's Boyles Law. And this is the before and after. So if you're trying to decide which one of the laws to use, you see which ones are held constant, and then look at the others as variables. If you're trying to figure out a decision-making procedure. Next, there was came the development of thermometer, a way to measure temperature reliably, consistently, reproducibly. A temperature system that was transferable over a wide area with a number of different scientists. They could rely on it, so that when you published your data, your research, then everybody understood what you meant by degrees centigrade. So that's Charles' Law. So Charles held pressure constant and moles constant, and let the volume and temperature vary. And what he found was these are two different constants, so I better do that. So when you have volume and temperature as quotient, one divided into the other, that's a direct relationship. Because in order to keep this constant, if this one goes up, that one has to go up. And you can use the same reasoning to use a before and after scenario. Like that. Okay? So how did Charles keep the moles constant? Well, he had a cylinder with a piston in it. And once you put that piston in there, and maybe it had a valve on the bottom, we just close it. Once you trap that gas in there, that's the same number of moles, and it stays that way through the entire experiment. How about pressure? How would you keep the pressure constant? You just put a weight bearing down on that, maybe a kilogram or something like that. As long as he didn't move to a different location, he knew that that kilogram provided a force that was constant. And remember, pressure is force per unit area. Right? So this area doesn't change. Right? Pressure there on that cylinder doesn't change as it moves. So the only thing he had to be concerned with was the force, keep the force constant. Okay, so I just add a weight there and I don't change the weight. So he had it covered. Pressure's constant. And of course, when you graph this one, a direct relationship, that you get a straight line. And let's see, who's next? If we hold pressure and temperature constant, and that volume and moles be the variables, we get Mikanos Law. So in this case, volume and moles are directly related. In other words, if you increase the number of moles in your container, you'll get a change in volume, an increase in volume, as long as you hold the temperature and the pressure constant. And then you can use the same reasoning and if you plot them, you'll get a straight line. Now, volume is easy to measure. How do we change the number of moles? Well, you have a valve, right? So you have a valve in your container. And we've got maybe a kilogram weight here. And we've got the temperature held constant in some form or fashion. So then you need a way to introduce more gas through a valve. And what you have is maybe another piston over here, right? And you know the volume of this right here. So once you open that valve, you just push that down, expel all that gas in here, and you know how much you put in, right? If these are exactly the same size, then you double the amount of moles in your container. If you double the amount of moles, you should also double the volume. That's the way you do it physically. But for chemists, the way you change the amount of gas is you have a chemical reaction. So let's say we have a certain amount of, let's see, I'm trying to pick a good example. Did we do one in here? I don't think we did one. What if we take ethane and oxygen? So this is, that's a gas. This is a gas, right? So we put them in our vessel and we let them react and we get CO2 and water. And at those temperatures, both of these are going to be gases. Oh, but we have to hold temperature constant, right? So this one's going to be a liquid. So the only gas we're producing is the CO2. So we just have to balance it. I don't know if I can do that with my head. Let's see. If I make 2 here, that makes 2 carbons. That makes 4 or 5 oxygens. But how about the hydrogens? Nope, we need 4 hydrogens. So if I make 2 here, so that's 2 carbons, 4 hydrogens. Now we've got 4, 5, 6 there. So that means we need 3 here. Okay. So that should be balanced. Now, how many moles do we start with before the reaction? 1 and 3 is 4. Right? Okay. How many do we end up with? With constant temperature, say if the temperature is like room temperature, then that's going to be liquid, so it doesn't count. It's a gas, it's not a gas. So we have 2 moles here. So we went from 4 moles to 2 moles. What's going to happen to the volume if pressure is constant? The volumes are going to be cut in half, right? We're going from 4 to 2, so the volume should decrease in half. And we didn't have to introduce anything else into it. Just that's in the container, hold the temperature and pressure constant. That's what you get. Okay, that's Avogadro's law. Now, you can also combine these. Hey, you can combine these into a single law. You have pressure times volume relationship, and then you have volume and temperature, right? So we put the temperature down here, and volume in moles, and put the moles down here, and that will be equal to a constant. That's the combined gas law. And then, of course, you can use the same reasoning to produce the before and after type approach. So this one, there you go. Now, in this case, you can say start off with these values, and then you only know 3 over here. You can solve for the one that's missing. Okay. That way you can let a lot of stuff vary as long as you know the end result, or you know the end result and you want to see where it started. It doesn't matter. This is algebra. All you need is one unknown and you can solve for it. Oh, got to back up. What units of measure do we use for temperature? Can't use centigrade. You have to use an absolute scale. And our choice is Kelvin. So the temperature has to be in K. And Kelvin is equal to degrees centigrade plus 273. So whenever you have a problem where you're going to introduce temperature as a variable, you should immediately convert centigrade to Kelvin. Now, if you have, if it gives to you in Fahrenheit, what do you do then? Well, Fahrenheit equals 9/5 centigrade plus 32. Sometimes they change 9/5 to 1.8, same thing. But with that formula, if you're given Fahrenheit, then you can plug that in and solve for this one. Find out what centigrade is. Then you add 273 to it. Okay, Boyles, Charles, Avogadro combined. We're still talking about laws. We haven't said anything about why this stuff happens. We say this is what happens. And these are all before-after approaches. Before, after, before, after, before, after, before, after. And before we go to theories, we can derive a formula that will give us the information we need, and all we need to know is what are the conditions right now. We don't have to know before and after. So if we take this one right here, PV over NT, that was getting weak. PV over NT equals a constant value. Okay. Well, if we pick our units, and for this class, we're going to use pressure is going to be in atmospheres. So at 1 atmosphere and 1 mole of gas trapped in our container, and standard temperature for gases is 0 degrees centigrade. So that'll be 273 K, right? And then under those conditions, we measure the volume, and the volume happens to be 22.4 liters. So atmospheres and liters, moles, and K are our units. And those will be the units for our constant value. And the constant value then is 0.08206 liter atmospheres, liter atmospheres per mole K. All right. We give this one a special letter. It's a universal gas constant. So if we do that and we say PV over NT equals R, we usually solve it so it looks like this. PV equals nRT. That's the way you usually see it. And the R that we're going to use is this one. You can use different R's depending on the calculation that you're doing. But we're going to use this one. And this tells you the units that each one of these have to be in. That's the only condition for using the ideal gas equation. That's what this is called. Ideal gas equation. You have to use the same units of measure that are in your constant value. So liters, volume, pressure, moles, and temperature. Then all you need to know is what are the conditions right now. So to that, this is constant. If we know this one, and this one, we can solve what's the temperature. Or if we know this one, and that one, say what's the pressure. Okay? So these are before and after scenarios, and this is right now. Okay. Any questions crop up? Still missing a couple. All right. So those are the gas laws. And then we went to the, actually, I think we got them switched around the way this, I just took these PowerPoints from the authors, and they put the kinetic molecular theory first. I think it's better to do the laws first because that's the way it happened, historically speaking. We got all the laws first, and then we try to explain them. And that's the kinetic molecular theory is the best explanation so far. So how would the kinetic, well, first of all, we need to define the kinetic molecular theory. It's got some postulates. Let's see. I'm going to have to erase some of this. We'll just keep the basic law structure here. Like that. And then we'll try to explain each one with the kinetic molecular theory. Okay, but we need postulates. Number one, matter is composed of tiny particles. Could be atoms, molecules, or ions, or any combination of those. Two, these particles are in constant random motion. You can always say that about any matter. The only time that they would not be in constant random motion is if they were at absolute zero, 0K, and we're never going to get there. So you can safely say that they're always in constant random motion. As you get colder, of course, the motion slows down. And corollary to this is the, let's see, I won't get ahead of myself. Yeah, I better not. 3. Actually, the 3 that they give you, okay, here's the ideal. The ideal situation is particles don't interact. That is, they smack into each other, they smack into the walls of the container, but when they do, they just act like billiard balls. They just bounce off. They don't attract, they don't repel. However, the real situation is they do attract or repel. And the way the authors describe it is they draw a distinction between potential energy versus kinetic energy. So that brings up the fourth point. These particles possess kinetic energy. Due to their motion, right? And you can calculate, for any one particle, you can calculate the kinetic energy as 1/2 times its mass times its velocity squared. But it's kind of difficult to do that for those tiny particles. So we sort of take an average. And we know that the kinetic energy is proportional to. That's what that means. Sort of a open-ended infinity sign. Kinetic energy is proportional to temperature. So we know that if the temperature goes up, kinetic energy goes up. Let's see. Right. So number 5 in your author's thing, it relates to this ideal situation. And that's the best way to describe that is elastic collisions. So when they don't interact, they just bounce off each other. Elastic collision, let me define that term. When two objects collide, an elastic collision means that the amount of energy that they had coming in is preserved. all the energy they had coming in, they got it combined going out. They don't lose any energy in the collision. As opposed to, let's say, Play-Doh. You roll up a nice ball of Play-Doh and drop it on the floor. What does happen? It's the floor, just stays there. Okay, all that energy that was stored due to its position is converted into kinetic energy right before it hits the floor. But when it hits the floor, all of that energy is dissipated as heat. Right? That's an inelastic collision. Okay, so this kinetic energy, the authors describe as disruptive force. That is, the kinetic energy tends to keep particles apart. In other words, the faster they're moving, the more likely they are to stay apart. And they want to push apart too. Potential energy is corresponds to cohesion or cohesive forces. That is, attractive forces that keep them together. And when they describe changes of state, the solid, the liquid, the gas, the authors are balancing one against the other. Right? So in a solid, the cohesive forces are dominant, and the kinetic energy is minuscule. In liquids, they're about equal. Kinetic energy is enough so that the particles move past one another and they overcome these cohesive forces that would hold them together into a regular shape. So they can't hold their own shape. And in gases, the kinetic energy is massive compared to the potential energy, so that all the particles they're just widely dispersed. And the cohesive forces are almost non-existent. Okay? All right. So let's look at these laws in terms of the kinetic molecular theory. So with Boyles Law, when the pressure increases, what does that actually mean? How does it affect the volume by the pressure increasing? Excuse me. Pressure, external pressure. Okay, well, actually, it's internal pressure too, because they're balanced. But if we, well, let's look at it the other way. If we change the volume, say we've got a trapped volume of gas at a known temperature, and then we add more pressure, what happens to the volume? The volume decreases because the pressure has to be balanced. Let's draw a picture. Okay. Say we start out here, and then we're going to decrease the volume to there. So these molecules are in there, and they're bouncing off the walls, and they have come to an equilibrium with the pressure. Right, so that piston stays put. Pressure inside, pressure outside is the same. And the pressure inside is maintained by collisions of the gas molecules with that piston. So if we increase this force, that piston's going to move until we get a balance of force from the bottom, from the inside. So how do we do that? Well, we need more force, which means we need more collisions, right? Because the temperature is constant. That means the particles are all moving with the same energy. So we need more of them, right? So as you decrease, that means the collision frequency goes up. You get more collisions on that piston, which increases the force and eventually balances again, and then the piston stops moving. That's the kinetic molecular theory explanation of this one. How about Charles? Well, if we increase the temperature of that gas, we increase the kinetic energy. So the molecules are moving faster, they got more energy, so when they smack up against that piston, they provide more force to it. So that means it's going to increase until the force is balanced again. How about Avogadro? Number of moles. We change the number of moles at the same temperature. Then we've got more molecules with that average energy. And more molecules with that energy means more collisions. More collisions against that piston mean more force. So the piston rises until the force is balanced again. So as it rises, we decrease the number of collisions on that piston, because we give the gas molecules more space to rattle around it. So once we reach a point where the collisions are balanced again against that force, the volume stops, the movement stops. So hopefully that explains at least these three laws in terms of kinetic molecular theory. Any questions so far? There's the gas laws. We've already talked about that. Okay, now we're up to Dalton's Law, partial pressure. It took how long to get there? Like 40 minutes? Don't want to erase that part. All right. Now we're up to Dalton's Law, partial pressures. Okay, simply stated, when you measure the pressure of a gas mixture in a container, you tap a gauge into it, you measure that pressure, you're measuring the total pressure. All the collisions of all the molecules in there against that meter, making the dial go over to a certain point. That's your total pressure. Dalton said that that pressure is due to the individual pressures of each of the identifiable gases. So if you have three gases, then you've got pressure from one of them, due to one of them, and pressure due to the second one, and pressure due to the third one. And they can keep going as far as you need it, depending on your mixture. But we're going to use three for an example. Let's say you have a mixture of nitrogen, oxygen, and argon, air that you breathe, right? So this one is 79%, this one's 20%, and that's about 1%. Right? And then you have minor gases in there, but they're almost insignificant. The total pressure, say at sea level, is 1 atmosphere. The pressure due to this one is going to be that many atmospheres, and this one's going to be that many atmospheres, and this one's going to be that many atmospheres. So you add them up, you get 1 atmosphere. let's see. Before we try to solve a problem, there's another way to express this. Each one of these can be represented, of course, by pressure, but these are also proportional to the amount of each gas relative to the total. And we give that a special value. Call it mole fraction. So if you were to have 1 mole of gas in that container and 0.79 moles of it was nitrogen, it would be 0.79 mole fraction. 0.79 of the whole. Oops. Okay. So the total is what? If you add all those fractions up, total equals 1. Right? If you add up all the fractions, they have to be a whole. Right? Unless you've missed one of them. If you add up the mole fractions and it doesn't add up to 1, then you're missing a component. Or your measurement's way off. One or the other. Okay. So I think we did this problem in class, the one with the 2 bulbs connected together, one at one pressure and one at another pressure, and they have different volumes. How do you deal with those?
Yeah, I think we did.
Could you solve that problem yourself? Let me make one up. Let's say we have a bulb here containing a gas, and it's connected to another bulb. Let's make it bigger. All right. So we're going to say this one is 5 liters volume, and this one is 10 liters. Okay. And this one is at 20 atmospheres. And this one is at 15 atmospheres. So they have to be pretty sturdy bulbs. That's a lot of pressure. Now, what we want to know is what's the final pressure after we open that valve and let them mix. Remember, when you mix 2 gases, what do you get? You always get a homogeneous mixture, a solution, every time. So they're going to mix. So what we're going to do is use 2 laws. We're going to use Boyles Law and Daltons Law of partial pressures. Because if you treat these as separate problems, let this gas expand into a vacuum, then that'll tell you the pressure due to that gas. And then let this one expand into a vacuum, and that'll tell you the pressure of that gas. Rather than making the same gases, let's make them different gases. Let's say this one's helium, and this one is hydrogen. About that. Then you can tell them apart. Right? So what's the pressure due to helium? Well, before and after. What's the before conditions for helium? Let's do this one. Because that's going to work for both of them. So for the helium problem, the before is pressure is 20 atmospheres. And volume is 5 liters, right? What's the after? We don't know what the pressure is. That's the unknown. But what's the after volume? right? 5 plus 10. Okay. Now we can solve for the pressure due to, actually, the pressure due to helium. Then will be, what's 5 times 20 is 100, divided by 15. 6.6667. Does that make sense? We're taking 20 atmosphere pressure and expanding it into an additional 10 liters. So the pressure should go down. It went from 20 to 6.67 due to helium. Okay? Now let's go the other direction. Hydrogen then would be, before is 15 atmospheres and 10 liters, and that's equal to the pressure due to hydrogen and the same volume. We're expanding it into 15 liters. So this is 10 times 150 divided by 15, well, that's 10. So the pressure due to hydrogen is equal to 10 atmospheres. Okay? And that makes sense. We're expanding 15 atmospheres into a bigger volume, so the pressure should go down for the hydrogen. Now we use Daltons Law, which will be pressure due to helium plus pressure due to hydrogen equals 6.67 plus 10 equals 16 point, well, let's see. I'm not using the right number of significant figures here. Round it off, say that many. Right. But if we rounded it off to 2 significant figures, then it'd be 17. But it's between 15 and 20, which is where we would expect it to be. Okay? All right, let's see here. Any questions so far? That's Dalton's Law of partial pressure. Did I give you the example for Dalton's Law of, no, I didn't. Another, a practical application of Dalton's Law. Or maybe there was a problem in your homework. The scenario is you're carrying on a chemical reaction and it produces a gas, and the gas is being routed through a tube into a vat of water, and we've got a container filled with water. So our reaction is in here, and it's producing the gas that's going in here and filling up this container, displacing the water. Right? And our container is calibrated so we can measure how much volume we're producing from the stoichiometry of our reaction. So we can track how much we have in there, and if we know the atmospheric pressure, because the difference between this and that is negligible, so we're just dealing with atmospheric pressure. And then we measure the volume, then we have the temperature, and we have the universal gas constant. We can find out how many moles there are. So we know how many moles of gas were produced in this reaction, and we can figure out whatever we want to do with the stoichiometry based on that. The problem is, we don't just have our gas in there, right? That space is going to have water vapor too. So we've got a mixture of two gases, the gas we're trapping plus water vapor. Right, so we can measure the total pressure would be atmospheric pressure actually. And then there's the pressure of our gas that we trapped plus the pressure of water vapor. So if we know this one, we need to know that one so we can find out what this one is, because that's key to our stoichiometry. So how do we find the pressure of water? Well, water is very well behaved. All we need to know is the temperature. If you know the temperature, then you can tell what is the vapor pressure of water in that space. That's it. Just read it off a chart. Find out what this is. Subtract it from this one, and you got that one. I don't know if there are any problems like that in your homework. But that's a practical application. Let's see. You coming up with any questions? Or do I just keep talking?
Is this being recorded like the other classes?
Mm-hmm.
Okay.
Yep, yep, you didn't miss anything. Well, you did, but you catch up. Yep.
Did you already give us, like, are we gonna do like a little extra credit assignment for these tests too, or?
Mm-hmm.
Okay, I just didn't know if you already gave it out when you said that.
No, you didn't miss anything. No, the extra credits were the periodic table and the nomenclature. Yeah, name the compound. Yeah. Let's see. Let's see if I got any that I've been hanging on to. Okay. Name the compound. I owe you that one. That's already been figured into your grade. Okay. How about the various processes? We got names for things as they go from one phase to another. So you can have, we'll put the gas up here, and we'll put a solid over here. Oops. Right. Put the liquid over here. Yep. And then we've got various changes going from one to the other. So if we go from gas to liquid, now let's go the other way first. Go this way, liquid to gas is called vaporization, right? Or evaporation. Evaporation, that's right. That's a better term. I want to use the terms that they're using.
Yeah, I use evaporation.
Evaporation. So what's the other direction? Gas to liquid. Condensation, right? Goes the opposite direction. How about solid and liquid? We'll go to solid to liquid, melting, right? And go liquid to solid, freezing. So the temperature at which this happens, the freezing point, is the same thing as the melting point. They happen at the same temperature. Or this one, liquid to gas is the boiling point. Right? So you can go from here to here to here in stages. What about this one, solid to gas? Think of dry ice, solid to gas. This is called sublimation. What if it goes the other direction? I think it's deposition. Yep. Okay. Those are the different processes for phase changes. Now the question becomes, which way is the heat flowing, right? Because heat has to flow in order for these to happen, right? We've got to change the kinetic energy, the average kinetic energy of the molecules to go from one to the other, right? So that means heat has to be transferred. So if we go from this one to this one, which way is the heat going? Heat's going in to evaporate, right? So that means endothermic. Condensation, when it goes from gas to liquid, heat has to go out because the molecules are slowing down. They got to give up some energy, right? So heat has to go out. I don't have any place to put it. It goes out. And that's exothermic. Heat goes out. So how about this one? If we go from liquid to solid, what are the molecules doing? They're slowing down, right? So that means they got to give up energy. That means this one is exothermic. And for melting, heat has to go in to speed up the molecules. This is endothermic. Okay? Sublimation, you're going from solid to gas. So you're adding energy. Molecules are moving faster to go from solid to gas. So this, we have to add energy in. Sublimation is endothermic. And deposition, they have to lose energy, slow down so potential energy can take over. Kinetic energy decreases. So this is exothermic. Okay? All right. What's next? How are we doing on time? 10:10. You got 20 minutes?
Yeah.
Okay. Well, the next thing in the list is vapor pressure. Discussion of vapor pressure. So, vapor pressure is the best illustration there is to have a container, an Erlenmeyer flask, and you put a stopper in it. And you have liquid down here. And you can have air there if you want, it doesn't matter, right? Because partial pressure means that if we put the stopper in there, then it's 1 atmosphere to start with. The vapor pressure is the pressure due to evaporation of the liquid, right? So it doesn't matter if you have something in there already. The change is going to be due to evaporation of that liquid. So you can measure that change. So initially, molecules leave the surface, right? Since there's none up here, when it first starts, they're all in one direction. It's a one-way street. But once you start getting more of them up here, then they start going back. So you reach a point where the evaporation and condensation happen at the same rate. And at that equilibrium point, equilibrium of evaporation, condensation. Yields vapor pressure. Okay, and it's a measurable difference, increase in pressure in that space. Okay. Now, the question becomes, does every liquid you put in there produce the same vapor pressure? The short answer is no. No, they all have different vapor pressures. So the question then becomes, why? Why would something have a higher vapor pressure than something else? The key is, what are the attractive forces in the liquid for the molecules? You know, is there something holding them down, keeping them from going into the vapor phase? Okay, so the stronger interactions here decreases the vapor pressure here because they're not as apt to go that way. So things like water, which is a polar molecule, they have very strong attractions for each other. So the vapor pressure up here for water will be low. But things like ether, that's dimethyl ether. The kind they used to use in the hospitals is diethyl ether. This is a nonpolar molecule. So the attraction of one molecule for the other in the liquid phase is very low. So that means there's not much holding it in the liquid phase. It evaporates, and this is all at the same temperature. It evaporates more rapidly and establishes a higher vapor pressure. So this is low vapor pressure, and this is high vapor pressure, based solely upon the attraction of the molecules for each other in the liquid phase. Okay? That's why when you open a bottle of water, or your Evian or whatever, well, water doesn't have an odor, but let's say water, you could smell water. You know, there's some animals that can detect very minute amounts of water. You wouldn't smell it. But you know, if you open a can of ether, you smell it like that. Right? The drive to vaporize ether is very high because there's nothing holding it in the liquid phase except the cap on your bottle. This is a physical process, physical equilibrium. Okay? Have we talked about chemical equilibrium? This is an introductory course. I don't know if we have or not.
I think you mentioned it. I don't know if you talked fully about it.
No. There's nothing in the program for their chemical reactions. We might talk about it a little bit when we get to chapter 9, chemical reactions. So I'll save that until later.
But anytime you have equilibrium, it's usually balancing one process against the other. In physical, in this case, it's evaporation condensation. For the chemical, it's you've got reactants to products, and they want to go both directions. Okay? So there's your equilibrium situation for chemical. We will talk about that later, hopefully. Okay. So what kind of forces? I mentioned polar and nonpolar, and we did talk about those. So what does it take to be, for a molecule to be polar? Two things. the bonds in the molecule have to be polar. So what does it take to be polar? Put simply, one atom bound to another atom have to come from different parts of the periodic table. The farther they are apart, left to right, top to bottom, the more polar the bond. That is, the more uneven the distribution of electrons. In fact, if you get the polarities so different, for instance, if you went from potassium to chlorine, the difference is so huge that you actually get a complete transfer of electrons from potassium to chlorine. You get an ionic bond. But if they're a little closer, say we had, I don't know, hydrogen and oxygen, like in water. The pull, the attraction of electrons is higher for oxygen than it is for hydrogen. Right? So we redistribute some of the electron density over here around oxygen, and that gives it a slight negative charge and a slight positive charge for the hydrogens. So you get polar bonds. Right? That's the first condition. The second condition is shape. What's the shape of the molecule? If water were shaped like this, with hydrogens opposite one another, those dipoles, we call them, would cancel one another out, and the molecule would be nonpolar. But oxygen's not shaped like that. Oxygen is shaped like this. So we have the dipole for that bond, and then when you add them together, you get overall like that. So we have negative that side, positive this side. Okay. Now that we have a polar molecule, when they're together in the liquid phase, they line up so that the negative side is attracted to the positive side, and you get a dipole-dipole interaction. Okay? In fact, this is a special kind of dipole-dipole interaction. It's called a hydrogen bond. The hydrogen bonds are at the upper end of the dipole interactions. They're the strongest of the dipoles. I think they mentioned hydrogen bond. Yeah, there it is. Now, continuing with that topic of forces, things that are holding molecules together. If you don't have a dipole, say you have a nonpolar molecule, like octane, you know, in your gasoline tank, right? It's mostly octane. Octane is an aliphatic hydrocarbon with a long chain of carbons, 1, 2, 3, 4, 5, 6, 7, 8, octa, 8 carbons, and hydrogen. Right, each one of those is a hydrogen. It is long chain. That is a nonpolar molecule. The difference between the polarity of carbon and hydrogen is almost nothing. Right? And the difference, of course, if you've got the same atom, then there's no uneven distribution, right? They pull equally. So there's no polarity here, and there's very little, if any, polarity there. So this is a nonpolar molecule. But octane is a liquid at room temperature. I mean, it has a substantial vapor pressure. I mean, anybody that's pumped gas knows that. You can smell it, get a little on your hand, and you smell it for days.
That's a nightmare.
Yeah. Or in the winter, if you're wearing gloves, you get some on your glove, you might as well throw them away.
If you have to store a canister in your car, you better hope it doesn't spill.
Yeah. So what is it that's holding them together in that liquid phase? Because there has to be some attractive force. something to hold them together. It's not dipole because it's nonpolar. It's a weaker force, but it's significant. It's called London dispersion. Okay? So what does London dispersion mean? London dispersion forces are instantaneous redistribution of electron density. Electrons are not fixed. They're in constant motion. So what happens is, for an instant, I mean a femtosecond, right? 10 to the minus 12th second. The distribution of electrons is such that you might have some more over on this side, which means they got to come from somewhere, so they come from this side. And if you have one of these molecules along here, right, then what does that do? Well, this positive attracts electrons from everywhere to here. And this negative, along with that attraction, turns this one slightly positive. Okay? This is happening just in the blink of an eye. When that happens, you get attractions. They come, they go like that, but they happen repeatedly. And the longer the molecule, the more chance there is for interaction. So longer molecules are liquid at higher temperatures. So diesel fuel, which has carbon chains that are like between 12 and 40 carbons long, has less vapor pressure, and it's liquid up to a higher temperature. That's why diesel is safer to use than gasoline, because it doesn't form that vapor as easily and mix with oxygen, and it has a flash point, things like that. So diesel is safer. But those are London dispersion forces, and that's why you have the liquids there. Now, it doesn't have to be a long molecule like that. We have London dispersion forces for noble gases too, right? So if you set up a chart for the noble gases, neon, argon, krypton, xenon. We'll leave radon off of there because it's radioactive. The boiling point is lowest for this one. In other words, you got to get it really cold to make it liquid. You don't have to get this one quite as cold. You don't have to get that one quite as cold. So this is the only one I know. I've memorized. 195 minus 195 degrees centigrade is the boiling point for argon. So this one's going to be a lower temperature than that and lower than that. But this one's going to be a higher temperature than that, and this one even higher. So how do we explain that? Because they're just molecules. Atoms. Right? Same thing, London dispersion forces. Xenon is a huge atom. Krypton's a little smaller, argon's a little smaller, smaller. So you've got more room to redistribute the electron density. Right. Less room here. So you're more likely to get London dispersion forces more frequently for this one than you are for that one, that one, that one. So the attractive forces are stronger as the atom gets bigger. So that explains why. That explains why you even have a boiling point for these, right? Because they don't form compounds. They don't play well with others. So one theory would say they're ideal. Their gas is all the way down to nothing, all the way down to absolute zero, but they're not, right? And we have to explain why that happens. And that's the explanation. London dispersion forces.
Just imagine the temperature it takes to freeze.
Oh, to turn it into a solid? Yeah. I don't think you can't get it down to here. Maybe they formed krypton as a solid.
Yeah, that'd have to be real
And
low.
xenon. Yeah, yeah. But these, no. You can't get it cold enough to make a solid out of these.
Even -1,000.
I think the boiling point for helium is like 4 degrees Kelvin, just 4 degrees above absolute zero is helium. Okay, so we'll have time next week to finish the review. Right. I was hoping we could get through chapter 7 today, and then we'd have the whole time to do chapter 8 next week. And we basically did. Unless you have some more questions, then we can talk about them.
We have a lab today.
Yeah.
Okay.
Or we could move right to lab.
I need to borrow someone's data for the lab.
Oh, the
Yeah, so I can,
Boyles Law.
yeah, so I can email it to you today.
Okay. Do you have it?
Yes.
Okay.
I have the data. I have to finish my graph where I had that math messed up, so I'll scan it and send it to you.
Okay. That works for me. So this is actually, today, we did chapter 7, and we'll do 8 next week. Okay, if there are no more questions, I'm going to stop this and let it grind its way through conversion. All right.